okay, or where you get energy. Okay, so in our story, that is where our charges, our electrons, our main, gets their food, gets their home, gets their energy. Then we have the charges, the electrons walking, and they are little men. So the charges are people, or you, and you walk in the circuit. Alright, so in a circuit, your battery, your cells are your home, and then you're going to walk through the home into the circuit. The circuit is the school. Okay, and in our school, the first place that you went this morning was register. So register is the ammeter. Is the register. And that ammeter, is register difficult? No, you go in, no, welcome, who's here, who's not here, who's absent, here's some letters, here's some forms, there you go. So register just counts. How many people are there? Right? Sometimes we have register at the beginning of the day, mostly, but sometimes we have it in the middle of the day quickly if we need to hand out letters or count again or something, or at the end of the day. So register can be anywhere. It doesn't take any energy. It's just passing through. You could also think of it as, you know, in some shops, especially like older shops, when you walk in through the door, it goes bing, bing. You know that? It's the same thing. It's just like a scanner of how many people pass through. Okay. Then the next thing that we have is resistors. Okay, I'm just going to make an R for a resistor. And the resistor is your periods. Maths, English, Afrikaans. Some resistors take a lot of energy. Yes, like science. Or not like science, I don't know, your preference. And some are easy peasy. Okay, so the resistors are periods, and periods takes energy. It uses energy. Then the second last thing is at home, where you get your food, okay, where you get your energy. We're going to say that energy that you get is, I'm calling it Nutella sandwiches. How do you spell sandwich? Rich. No, that's a witch. Yeah, sandwich.
No, I don't think there's an H.
Okay, well, doesn't matter. You can choose whatever. If you want to make it a hot dog, you make it a hot dog. If you want to make it a chocolate, you make it a chocolate. When I came up with the story in high school, I wanted Nutella sandwiches. You know Nutella? On what bread? Laka. Alright, so you can call it whatever. My energy is sandwiches, Nutella sandwiches, and it's true, there's no H there. Okay. And I get that food at home. So I pack it in my bags in the morning, then I walk to school. I don't use it in register, but then I use it, let's say I have 2 periods for the day. Let's say I have maths and Afrikaans. Then maths a bit difficult, so I will use, let's say I had 10 sandwiches. Then for maths I'll use like 7 sandwiches, and for Afrikaans like 3 sandwiches, and then I go back home where I get 10 more sandwiches. Alright, so that is the idea of the sandwiches. And then lastly, the thing that we're going to use is a voltmeter. Okay, and a voltmeter is Miss Phsc. Okay, do you know tall Miss Phsc that teaches LO? Yes? Did you know she's our school's counselor? Right, so those of you that don't know, if you're having a bad day or if something happens in your life or whatever, it can be small like you did not do well in a test and you're having a bad day, or it can be big like someone passed away or bigger, whatever it is. And then you can always go speak to her. She will keep it confidential, and then if she can't help you, she will get someone from outside, a social worker or what, to assist you, to help you. Okay, so this is Miss Phsc. What does she do? She checks if you are, checks energy. Okay, this was actually supposed to be written here, but anyway, it doesn't matter. She checks your energy. She checks to see if you are okay. What is your energy levels that you have left? All right, so let's see if we have a circuit. Right, that is our circuit, and let's say we have math and we have allo. All right, and let's say you that are going to walk through in your backpack, that is not a cape, that is your backpack, you have, let's say, 3 sandwiches, 1, 2, 3 sandwiches for the day. All right, so you're going to walk from the positive all the way to the negative, so you're going to walk in this direction. And when you leave the home, how many sandwiches do you have in your bag? 3. 1, 2, 3 sandwiches. Okay, so at home you get your energy, you get your volts, you get your 3 sandwiches. Then you walk through register. Do you use any of the sandwiches in register? No. Okay, you just walk through. It just counts beep, 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 beep. How many people are there? Walk, 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 walk. Now, when you plan for the day, you check your timetable, you see, oh, today I have math and life orientation. All right? Are you going to split up your sandwiches equally, 1.5, 1.5? No, because it doesn't take the same amount of energy for both. Okay, now I think you all agree that math will take more energy than allo. Yes? Some people really dislike allo, but that is the exception. Okay, so if you had to plan your sandwiches for the day, you would be like, okay, I have 3 sandwiches, math and allo. So I think I'm going to take 2 sandwiches allo and 1 for math. 2 for math and 1 for allo. Right? If I have to split it up. So you walk here. How many sandwiches do you have before math? 3. Okay. How many sandwiches do you have after math? 1. Because you used 2. Okay, and that is what Ms. Phsc does. She, as the voltmeter, doesn't take sandwiches. She just quickly looks in your bag before math. How many sandwiches? Or what's your energy levels? Are you okay? Oh, you have 3 sandwiches. After math, checks in your bag. How many do you have? Oh, you have 1. So then a quick calculation, and she sees you used 2 sandwiches for math. Alright, so my question now to you is, if a voltmeter is connected like this, a voltmeter is connected in parallel, can the little men, you guys, that walk, there you walk. Remember, there's not just one of you, there's 13 of you. If you walk, can you walk through Ms. Phsc? You can try, but you can't. Okay, so you can only pass through math. You can't pass through Ms. Phsc as well. So everyone needs to go through there. You don't have a choice. Right? Then you get to allo, and Ms. Phsc quickly checks in your bag again. And before allo, how many sandwiches do you have? 1. After allo, how many do you have? 0, because you go home where you get 3 more sandwiches. So this voltmeter will read 1 volts. Who brings food to school? Alright, Adleam, who packs your food for school? You. Who makes the food? Okay, and if you bring the food back home, or you take the food back home in the afternoon like you didn't eat it, will he be upset? Alright, so you can't leave food there when you go home. I know my mom checked my bag every day, and I think it happened twice that I didn't eat her food, and then she stopped packing food. I had to pack myself. So you can't, so we will always have 0 left when we go home, because you can't take food home, because there you get 3 more and you follow the same thing over and over and over and over and over again. Alright, so what we see here is 2 things. We see that these 3 sandwiches, all of the energy that I have at home, I plan for the day and I split it up, how much I will need where. So I see that I split up my energies. I had 3 volts and I split it up into 2 and 1. So 2 plus 1 gives me 3. Then the other thing that I saw is in this circuit, we call it a series circuit. Why? Because the little men that walks here only have one path where they can move. Nowhere they can split up and go a different path. So we call this a series circuit. Okay, now I have space next to it. You don't have space next to it at the bottom, on the next page, it doesn't matter. The next circuit that we're going to look at is a parallel circuit. Oy. Okay, it's a parallel circuit. Right, now in this parallel circuit, let's say people have a choice between math lit and math. Okay, and again at home, you get 3 sandwiches, 3 volts. Okay, so here you walk with your 3 volts. Do. Everyone needs to pass through the ammeter. It's registered. It checks how many people are there. Now, let's start Omalemo with you. Let's say you choose to go to Mathlit. Okay, so there you go. How many sandwiches do you have before Mathlit? 3 sandwiches. And after Mathlit? Okay, let's check. Where do you go after Mathlit? Can you go to math? No, because then you go in the like opposing current direction. So after Mathlit, where do you go? Back home. So how many sandwiches do you have after Mathlit? None. 0. So if ma'am checks there, what is your volts status, your energy status, it would be 3 volts. Okay, now Asina, let's say you choose math. So here you go. Before math, how many sandwiches do you have? And after? Hoekom? No. Where are you going after math? Back home, where you get 3 more sandwiches. So you have to eat everything. Okay? So can you see that even though some people go to math, some people go to math, they get the same amount of sandwiches. Why? Because they are parallel to one another. What will be different between the two is the amount of people that choose to go through there, the amount of charges that walks through there. Because as we can see from this class, how many are you in this class? Like in your class? 36. How many chose to take math? In my class you are 13. So 16. So out of the 36, 16 chose math and 20 chose math lit. And we know from experience that that will also change a bit until matric. Right? So we can see that a lot or the most, the bigger percentage chose math lit. Why? It's easier. It's less resistance. Okay? If I told you that you can go study anything you want, if you have math lit, would you still choose math? No, because you'll get a higher mark when you do math lit. It will be easier. It won't be such hard work. So why would you choose the difficult path? So same thing here. Because it is easier, because math lit is easier, or because this resistance is lower. Let's say this resistance is 1 and this resistance is not. Let's not go 1 through. Let's say this is 2 and this is 10. Because it has a lower resistance, more charges will go through here. So if we say let's say there's 100 charges that pass through, then about 60% will go through this one and about 40% will go through that one. All right. So even though the volts are the same, the energy that you have to pass through, the number of sandwiches in your backpack will be the same, but the number of people that pass through there will be different. Sharp. Okay, right. So back to your notes. So that's the introduction. That is what we are working towards. And I'm going to refer back to the sandwiches and the little men and the registers and whatever. All right, so electricity. Okay, what is electrical current? Electrical current is charge in motion, charge moving. So we said that's current. We said static electricity is charges that are stationary, that are static. And electric current is charge in motion. Now this charge is different for different things. For us now, we are going to look at electrons. Electrons moving, and that we get in metals. That's why our conductors are made out of copper or chrome or whatever. Right? But you also get different other charges. You also get, and we're not going to do them now, we get ions that move in liquids or in aqueous solutions. And you also get electrons, ions. It's also called ions. Ions that move in gases, but it's different types of ions. So the gases that are here in these light bulbs. Okay, but these two are different types of ions, but it doesn't matter. All right, then an electrical current can only flow. Okay, so we can only have a current, and now there's conditions. If we have two things. If you have a source of energy, something giving food, cell, battery, whatever, and if you have a closed circuit. You do not have to have an ammeter. You do not have to have a voltmeter. You do not have to have a light bulb. You don't need any one of those things. You just need a closed circuit, a wire, and a battery. Right. Then we are going to look at conventional current. Conventional current. Conventional current, you did this in grade 8 and 9, is where positive charges flow from the positive pole of the battery through the circuit to the negative pole of the battery. But wait a minute, ma'am, didn't you just say electrons? Electrons aren't positive. Now you speak about positive charges. Okay? When they set up circuits, they set up voltmeters, they set up everything, they thought it was the positive things that move. And after a lot of investigation, after a lot of years, they realized it's actually the negative electrons that move. Okay? But that doesn't matter. Everything works, so we still go with the thought process of it's the positive things that move from the positive pole through the circuit to the negative pole. So if they ask you for conventional current direction, that is what we're going to say. If we look at what's actually happening, it's electron flow from the negative, but we're going to look at conventional current from the positive. It's wrong. If I ask you, what is conventional current direction? Okay. If I ask what is the electron flow, then you're going to tell me that one. Right. Then a few things here that you should have seen before. That is a battery. Yes. This is a switch. This here is a lamp or a light bulb. You've seen a voltmeter, ammeter, resistor. You've seen? Then a variable resistor. Never heard about that. It's also called a rheostat. A rheostat. Okay, now that is the symbol for it. Now you might, some old textbooks or some older people or whatever, draw a resistor like this. Have you seen that? Okay, that is old fashioned. We don't do that anymore. We draw it like this. Okay, or they draw a variable resistor like this. Like that, with like an arrow at the top. That is a variable resistor. But like I said, these two are old symbols. We don't use them anymore. Okay, we use this block and a block with an arrow through it. Now, a variable resistor or a rheostat is something like this, where you can change the resistance. Okay, when in your everyday life do you use something like this? Every day, huh? A stove. How warm do you want the stove? Do you want it to be cold or warm or very warm? Where else? Lights, if you have dimming lights. Where else? The radio or music player or your cell phone to go up with the volume or down with the volume. Stove, if you use a toaster, yes? Okay, good question or good comment. A microwave uses microwaves. A microwave does not use an element. Okay, so there is a change, but it doesn't change the resistance of the element. Okay, but we'll get to that again a bit later. There's lots of places. A fan like this, how much do I want it to turn? How fast do I want it to turn? So a rheostat you actually use like for everything, I want to say. Right, and then the last thing there is an electric motor. It's not something we use a lot in our science class. It's something we use a lot in every day because there's a motor in there. There's a motor in here. There's a motor in here. Where else do we use motors? In there, there's a motor. So a motor is something that turns. Alright, but we're not going to use it in our circuit diagrams in science class. Right, then the next thing there is electrical current, potential difference. Electrical potential difference. And the abbreviation that we use is PD. Potential difference. Okay, now let's read this sentence. It says there, the definition. It is the energy transferred per unit electrical charge flowing through a conductor. Energy transferred per unit electrical charge. Okay, so let's just quickly look at that. When I say the word per, what must you think of? Not a cat. Not one. Yes?
4F or something.
Yeah, but I said when we were busy with waves, I said from now on until the day you die, when I say per, you must think of something. Yes. Division. Okay, so the word per means divide by. Okay, so what must we divide by what? They said the energy transferred divided by electrical charge. Okay, now we've done electrical charge. Electrical charge is measured in what again? Coulomb. And what was the symbol for charge? No, that's the symbol for the unit. What's the symbol for charge? Q. So it's Q. So we must divide something by Q. Electrical charge per electrical charge. We must divide energy by charge. Okay. Now energy we get at two places. Or energy has two symbols. Energy symbol is either E or energy symbol is a W for work. Because to be able to do work, you must have energy. Okay, and the one that we're going to look at in this chapter is E. So we're going to say W divided by Q gives you potential difference. Okay, so what is potential difference? It's the energy per electrical charge. The energy per electrical charge gives you what? Gives you the potential difference, and potential difference is your volts. Okay, so this is where we get to this formula. So in science, most of the time, 90% of the time, okay, you have that in front of you. 90% of the time, this formula that you see in front of you there has a definition that goes with it, and the definition and the formula is linked to one another. They should help you. This formula will be on your data sheet. So if I ask you, what is the definition for potential difference? You're going to go, okay, volts is potential difference. It is the energy per charge. You see that? Okay, now you need to fill in all the fancy words. So it's the energy transferred per unit electric charge. Okay, so there on the right hand side, you see there, V is the volts, or the potential difference measured in volts. W is the work done in joules. Joules is the unit for energy. And Q is the charge in coulomb. Sorry, I just want to check something quickly. Right. Then the next thing there is, where do we find these, or this potential difference, this volts? It is stored chemical energy in the cells. Okay, so cells store chemical energy, and we're going to do a chapter in grade 12 where we see what chemicals do we put in a cell, what chemicals gives you volts. So stored chemical energy is converted to electrical energy. So here in the cells there's chemicals, and it's converted into electrical energy as soon as the charges start to move. That enables charges to move through the circuit. Okay, why does a charge lose volts? Why do you use volts? Why do you give it away when you go through maths or allo or whatever? It is because there is resistance. And what causes resistance is when there is collisions with particles. So when it's like there's an open path, and when they get there, it's like they need to squeeze through to actually pass through. Okay, and when they squeeze through, they collide with each other, and they bump, and they lose energy. Okay, so that is why they use energy. Why would we do that with charges? Is some components, let's say this thing here, how much volts comes out of our plugs? Do you know? It should be 240, it's more or less 220 because of self-induction, blah, blah, blah. But this thing can't handle 220. It can handle less. So we put in resistance here, or resistors, so that the charges struggle to pass through, so that little bit of charge pass through each time. Okay, so that this thing does not get too much energy and it explodes. Okay, so that is why we put in resistors, is to control the circuit, to not let too much current pass through, then it's going to explode. Okay, so in these resistors, the particles collide with each other, and then the electrical energy is converted to heat energy. That's why things heat up, because the particles collide. Imagine you doing this the whole time. What will happen to your hands? Your hands will heat up. All right. Then, this potential difference, okay, only exists where energy is added or where electrical energy is used. So you can only measure potential difference where you add energy or when you use energy. Okay, ma'am, please explain. I can only get a voltmeter reading where I use the energy or when I add the energy. Okay, now you can see here there's 24 volts, 24 sandwiches. Now let's say I put a voltmeter in here. Right. Where am I? To me. How many, where's your glasses? Again. You can see now. I know, that's why I zoomed in. I knew your question was coming. How many sandwiches do we have there? Remember, positive to negative. How many sandwiches do I have here? Okay. And relay, how many do I have here? 24, because you haven't used anything. So, Amora, what would the reading on this voltmeter be? Okay, so what does this measure? It measures the potential difference. Is there a difference between there and there? No. So what will the reading be? Okay, wait. This voltmeter here measured the potential difference. How did we get to 2 volts? 3 minus 1. What would the reading be here? 0 volts. Okay, so that is what I mean when I say you can only measure potential difference where you add energy or when you use energy. There where nothing's happening, the potential difference will be 0. Even though there is sandwiches, I'm not asking what is the volts, I'm asking what is the difference in volts. Okay, right. Then we measure potential difference with a voltmeter that is connected in parallel. Okay, then I want to skip that bullet quickly. Then it says a voltmeter has very high resistance. Voltmeter has high resistance. That means that no current can pass through it. Okay, I'm going to zoom in. So what do we mean here is when the charges get here, they don't have a choice, are they going to split up there and there? Because they can't pass through the voltmeter. You can't pass through Miss Phsc. Okay, it's impossible. The charges can try and then no, they have to go back there. Okay, so the voltmeter has such high resistance, it's like a closed door. You can't pass through there. Right. Now, have you seen a voltmeter in your life before? Never ever. Alright, so this here is a voltmeter that we use in class. This is not what all voltmeters look like. Alright, but a voltmeter that we use in class. So here you see there's a black socket and a red socket. Alright, the black socket we always connect to the negative side of the battery, and the red socket always to the positive side of the battery. Okay, so if I were to connect it here, then I would, let's check. Where is the positive side of the battery? Here is the positive side. So then this one must be red, and then this part must be black. Okay, are you with me?
Yes.
Right. Then we can have 24 volts, we can have 3 volts, we can have 1.5 volts. We can change the amount of batteries. Then we need to change the scale of this. Okay? Let's imagine we have 3 scales in our life. First one, this is a scale that we use in chemistry. This scale is very expensive. It's about 2,000 rand for this one here. 255. Anyway, this one can measure, the maximum is 220 grams. If you measure way more on this, then it will break. Yes? If you put a 2 kilogram block on here, it will break the scale. Right, then in our life we also have like a normal scale that you have at home that you step on to check your weight. And then we get these big scales that like a lorry goes on, and to where the lorries are too heavy for this car, for this road or whatever. Alright, now let's say I want to measure my body weight. Can I stand on this one? No, it will break. Can I go stand on the one that measures a lorry? No, you'll get a reading, but it will not be very accurate because my weight is too small relative to the lorries. So I must get the appropriate scale for what I'm measuring. Okay? The same thing here. Here we have 3 scales. At the bottom, it says 3, 10, and 15. So let's say I have batteries that's connected, and the batteries are 12 volts. Can I put my red socket in there? No. What will happen is this needle at the top here will go there and it will break the scale. Okay? So if I'm unsure what my reading will be, like I'm guessing, I don't know, you always start with the biggest scale first, and then when you see, oh, my reading is too small, I can't get a nice reading, then you go to a smaller scale. Okay? Otherwise you break the apparatus. So that is what it says here. When connecting voltmeters, observe polarity, check the black and the red, and then use a larger scale first and then change to a smaller scale if needed. Right, so we are going to do a class activity where we are going to check the volts. Okay.